Welcome to note set number 4, where we'll talk about system modeling and some examples of systems. So there's a physical view, circuit board with some wires where you can apply an input and an output. We might have a schematic view of our system where we see circuit components and how they're connected and their values. And we see that here we have an input signal as a guitar, and here we have an output signal where the load is actually considered to be part of the amplifier that this might be connected to. So those are two different ways to think about models of the system. In fact, the top one is the actual system. Then we have an actual model of that, which is how we connect the components. What we're interested in, though, is something more abstract that allows us to actually go from this direction to that. That's the engineering design process. So we need to have some way of modeling how this system is going to behave before we actually build it. And so before we can start figuring out what kinds of circuit configurations we would use and what kind of component values, we have to have in mind what this system's going to do, and mathematically how do we characterize it so that as we come up with some possible circuit schematics, we could then translate each of those into some characteristic mathematical model, and then we can actually try it out. So if you've used PSpice to simulate and model circuits in a circuits class, perhaps, that's exactly what it's doing. It's taking the schematic and converting it into a math model, which then you observe how it behaves, and you go back and change how the schematic might be configured, and then do it again. And so you have this cycle of analysis and design. But from our point of view, we want to focus on the tools that we use to mathematically model the input, mathematically model the system, and then mathematically model the output, so that we can say, if I have a certain system with this math model and I put this input in, this is exactly what I expect to get out. It allows us to predict how the system will work and understand why it works the way that it is working, so that when we do get to the point of actually building the system, we've got a good chance of it doing what we actually want it to do. Now, the main math model for physical systems is differential equations, and there's a reason for that. That's because the physics of electrical components depends upon derivatives. So you've seen in your circuits class that capacitors and inductors, their current and voltage, are related with derivatives. Yeah, there's an integral form for each of them, but the derivative form is the more useful form for what we're interested in. Resistor is the odd one out. It is not a derivative relationship, it's a proportional relationship. So if the world was made up of just resistors and things that worked like resistors, where one quantity is related proportionally to another, we wouldn't have differential equations. But we also wouldn't have a lot of other interesting things that we have in this world. It'd be a pretty boring world, actually. So it all boils down to device rules that depend upon derivatives. And that leads us to a differential equation. I show here a second order differential equation because the highest order derivative on the so-called left-hand side is 2. And so by convention we put our so-called output variables over here, and these are our input variables. So the idea with a differential equation is you tell me what x is, so I plug x in here, and then it's a puzzle. I have to find the y that when I plug it in there for the given coefficients and the given input, so that it all makes an equality on both sides. So given the input x, find the output y of t. That's what it means to solve the differential equation. Now, as you've probably had differential equations, hopefully, or at least some exposure to that, you know that solving differential equations is not an easy task. And so engineers and mathematicians have come up with other math models that allow us to solve differential equations in a way that we can understand their behavior and predict how they will behave in many different situations. So some of these tools I list here. The names won't mean much to you now, but by the end of the course we will have covered all these things. So things like frequency response, transfer function, Fourier transform, convolution. These are all things that we will learn about, but basically they all get back to differential equation. This is for continuous time anyway. Notice we're talking about continuous time signals. So our goal in engineering is to be able to predict ahead of time, before we build this $1 million system for the government, for the Department of Defense maybe. We want to be able to predict this is how it's going to behave and this is how well it will work before we spend all the money doing it. So we need to be able to accurately predict the quantitative behavior of a system, and so that's what leads us to use these math models. So for circuits, just limiting ourselves to the passive components, resistors, inductors, and capacitors, we know what their device rules are, how their currents and voltages are related to each other, and we also have our circuit rules. That's how the rules of the road, so to speak, for when we connect devices together. So regardless of what devices there are and how we connect them, they have to follow certain rules, in particular KVL and KCL, and then special cases of that, the voltage divider and current divider, and so on and so forth. So if you combine the device rules and insert those into the circuit rules, and then manipulate things around, bam, you get a differential equation. Now the mechanical engineers, they've got the same thing. They've got their device rules, and I'm only showing the classic devices, quote unquote, mass, spring, and damper. And you'll notice that they have a proportional one, they have a derivative one, and they also have a double derivative one. So things are a little bit different, but actually not that different, to be honest. And then they have their system rule. So sum of forces is kind of their Kirchhoff's law. And if you fuse those together, again, you get a differential equation. So both sides you get differential equations. Now the interesting thing is that if you go to hydraulic systems, chemical systems, all sorts of different systems, and even combinations of these, you're still going to end up with differential equations. So to coin a phrase, differential equations rule the world. So let's take a little example here to see how, and even such a simple idea of sending information, digital information, over a wire cable between two computers degenerates, quote unquote, very rapidly into solving a differential equation. Let's see. Okay, there we go. So we've got two computers. We've got a pair of wires here connecting them. We can think of those two wires being close and together, separated by an insulator. So two conductors separated by an insulator is a capacitor. And also each length of wire has a certain resistance. The longer the wire, the more resistance that's going to have. So suddenly we've got resistance and capacitance involved here. We're going to assume that there isn't any inductance, but if we had like a twisted pair, which is a common way of doing physically configuring these wires, two insulated wires twisted together, there might be some small amount of inductance which we could model, but we're going to ignore that. So some typical values: 100 ohms per kilometer and 50 nanofarads per kilometer. So we're not talking about a lot, especially if we're doing a short distance here, but we're talking about some, and in order to perform a high performance transfer of data, we need to take these things into account. Another possible type of cable is a coaxial cable, where you've got a center conductor, then insulation, then a cylinder of conductor around that, and then more insulation. So also in either of those cases you get resistances and capacitances. So the resistance as well as the capacitance increases with the wire length. So here's our simple model now. We're modeling the resistance in the wires by R, the capacitance between the two wires by C. We're modeling our transmitting computer by just switching between 0 and 5 volt level, and we're modeling our receiving computer as an infinite input impedance. So you probably haven't yet gotten all this in your circuits class, and maybe you'll start to see this in your electronics class, but let me be let me just lay it on the table here. Our goal in connecting parts of a system together electrically, we look at the Thevenin equivalent circuit of our driver. We don't care about what's behind all that. We just care about what is its equivalent output voltage. That would be its Thevenin voltage. And what is its output resistance? That's the so-called Thevenin resistance. So we're going to model this in the ideal case, something that's driving with voltage. Ideally will have a low output resistance, a low Thevenin equivalent resistance. And on circuit specifications, system specifications, you can often find that specified as output impedance or output resistance. So we're going to take that to be 0. We're going to model our cable by a very simple RC model. And then the receiving computer we're going to model also ideally with an infinite input resistance, so that no current is being drawn off through this path. So what that does is it leaves this in isolation. Hanging the second circuit, or the second computer, onto the output of the cable doesn't change the analysis of the cable. If this receiving computer didn't have infinite input resistance, then we'd have a resistor here, and we'd have to account for that in our analysis. So by assuming this ideal case, we've eliminated that. In a real world, you'd have to account for all that. So here's our scenario. We've got our simple schematic diagram, simplified now, with some voltage source, and we're going to assume that that is just switching back and forth to represent a sequence of 2 zeros, then 2 ones, then a 0, a 1, and so on, by just flipping back and forth between these levels. We're going to ignore how that second computer can figure out where the spacing is between two consecutive symbols, but there are ways to do that, but we're not going to worry about that for now. Our goal is to try to get this signal over to here, or over here, as undistorted as possible. So again, just repeating what we saw in the previous chart, and now we're going to analyze this, and we write our loop equation. So this is just KVL around that loop, and then we have each of those described, each of those components described by their device rules. And then if we just plug all this together, you learned how to do this in your circuits class. I would expect you to be able to do simple ones now. You plug all this together and bam, you get yourself a differential equation. And so now, given this x of t, we plug it in here, we need to find the y of t that satisfies this differential equation. Seems simple, but may not be that easy given such a complicated and involved input signal. You've not seen anything like that before. But you do know how this circuit behaves. Suppose this just went like this, 0 and then went to 1 and stayed. You know how that circuit, that RC circuit, behaves to that, right? It starts charging up, and it'll charge up to at some rate and then stay. So if that were the case, what would happen? Well, it starts to charge up. It's essentially there, and then now it starts to discharge and charge. And so actually we can get a rough idea of how this thing's going to behave just from our previous knowledge. But we'd like to be able to come up with a nice, precise mathematical way to describe this. Engineers need both of these kinds of viewpoints. Rough seat of the pants, kind of a rough understanding, as well as precise understanding. So we need to solve this thing. But this is a linear system. We know that it is because it has only R, L, and C components. And so we can analyze it by superposition. Now in your circuits class, you use superposition to say, I've got one source here, I've got another source over there, I can treat them separately. We've only got one source, but it's a complicated source, and we can break that one source down into a fictitious imaginary sum, made up, envisioned sum of other sources, and then we can consider each of those individually. So we decompose this given input into a series of shifted unit step functions multiplied by 5 volts or minus 5 volts. And so you should be able to convince yourself that if you add these things together, that you'll get this little sequence of ups and downs. So that's nice, but now we know how each one of those input components goes through this system. In other words, we know how to solve the differential equation for this very easily. So we learned how to do that in circuits class, and the blue diagram or the blue curve shows that. And we also know how that one goes through. It's going to go like that, and like that, and like that. So if these, by superposition, if these add up to give us the input, then these blue ones must add up to give us the output. That's the idea of linearity, which we'll talk more about in a little while, but that's also the idea of superposition that you've already seen. So those are our individual output components, the blue ones, not the red ones. And when we add those together, we get something that looks like this. So we can write a math equation for each one of these blue ones, and then on a computer we can add those all up and find out precisely how this thing works. And yes, sanity check, it behaves just like we expect it to. Now, an even bigger seat of the pants idea is this RC circuit that we see. A cable has the effect of smoothing out the hard edges. Now, if we were to make the RC time constant even slower, so the circuit responds even slower, then we would see something like this. This would go up slower, and this would come down slower and slower. And now we have a case where we can barely even tell when we're switching from a 1 to a 0. Or equivalently, if we tried to switch this thing for the same RC that as we analyzed here, if we tried to switch this thing faster in time to send at a faster data rate, now we need a cable that will respond even faster. So this allows us to understand why a cable of a certain quality, certain R and C components making up the resistance and capacitance in the cable, are going to provide impart a limit on how fast we can send data over that cable. Big idea. So here's what we just did. We went from a physical system to a schematic idea to a mathematical idea, and then we could solve that mathematical system. That's what this course is about. Eventually you're going to get back to here and build cool stuff. But in order to make that cool stuff work as well as possible, we need to be working down at this level and be able to do it. So here's the big picture for continuous time systems. It's all about derivatives. Derivatives are everywhere in the world. And so we have differential equations that we have to deal with. Fortunately, we're going to limit ourselves to the easiest ones: linear, constant coefficient, ordinary differential equations. There's an awful lot of stuff out in the world that can be very accurately modeled with those. Okay, now moving on from continuous time to discrete time. we're now talking about computer processing of signals and discrete values that have been collected. So let's illustrate this with an automotive example. Suppose we've got a sensor on our car, and every 10 seconds it tells us this is the instantaneous miles per gallon. Let's not worry about how it does that, but suppose over some very short period of time it measures how much gas you've used to go some very short distance over a short period of time. So we get that measurement every 10 seconds, but what we'd like to do is be able to display the average miles per gallon over a much longer period of time from when we reset this system to now. And that should go cumulatively as time goes on. So maybe you've ridden in some of the hybrid cars, and even non-hybrid cars have this as a display. And you can see an instantaneous miles per gallon, but you can also see your average miles per gallon since the last reset. That's what we're interested in here. So assume that x of n is our input. That's the sequence of these instantaneous mile per gallon measurements. And since our sensor is giving them to us only every 10 seconds, this is a discrete time signal. And let's just wish into existence some output y of n, and that's the average miles per gallon at the nth measurement. So from time equal to 0 when we start this thing, all the way up to whatever our current n is, that's what we're displaying. And this thing will go with, keep showing and accumulating this. So at the nth time, what we could just do is take all of our measurements, there we go, add them together and divide by how many we have. Since we start here at 0 and we go up to n, we really have n plus 1 measurements. So we have to divide by n plus 1. Okay, good. But how much memory should we implement? We don't know how long this is going to run. We don't know when the person's going to hit reset. So maybe we need to have lots and lots of memory. Well, how much is enough? That's going to put a limit on when the person can hit reset. There's a better way to do this. So let's look at this mathematically. All I've done is rewritten what I had up above and just regrouped things and played a little trick right here. N times 1 over n is 1, so I've just artificially inserted that. But by doing that, I get this to be the previous average. That's my output at time n minus 1. So look what I have to do. I take the previous output value, multiply it by a number, multiply by a number, and add in my new input. And so this thing is actually what's called a difference equation. It's very similar to a differential equation, but in discrete time we don't have derivatives because we can't do those let epsilon go to 0 kind of things. But this is a difference equation, and it behaves very similarly to a differential equation. Now, we can easily implement this thing in software or even in hardware. Here's some MATLAB code to do that. We'll talk more about MATLAB later, but I know that you've been exposed a little bit to MATLAB. In a real system, you would do this more as a while loop than as a for loop, but I just left it as a for loop. And this is just showing, as time goes on, for a particular set of input values, how we would calculate this. So this is very simple to implement. And if we wanted to do this more in a hardware kind of way, we can do it this way. The input value gets multiplied by this number. The memory stores our most recent output value, and then that gets fed back, multiplied by this, and added together. So there has to be a clock that goes on. Every time you get a new input, everything gets clocked here. So you get a new input, the clock hits here, the clock hits here, the clock hits here, and the clock hits here. So when the clock hits here, the output is applied to here and gets multiplied and applied to there, and then they get added together. So you could implement this thing with just a handful of simple digital logic components. So our big picture here overall, we illustrated a discrete time system that gets modeled by a difference equation, and we'll see that difference equations are a very general form, more than just doing average mile per gallon. They are a very fundamental way of modeling discrete time systems. And for continuous time systems, we have differential equations. And even though we haven't seen this yet, you know from your differential equation stuff that there is a homogeneous solution and then what the mathematicians often call the forced response. But there are two parts to the solution. The part when the input is set to 0 and there are some initial conditions, and then there's the 0 state part, which is due to the input. So we'll talk more about these two parts later, but our biggest focus, at least first, will be on this 0 state response. We'll assume that our systems have 0 initial conditions. So if you remember, for differential equations, that had to do with the output value, the first derivative, second derivative, and so forth at the time that the input is applied. Similar ideas hold for the difference equation viewpoint. But in both cases, we're going to not be worrying about those initial conditions. Physically, that means our system is sitting there, especially in the continuous time case, it's sitting there with no stored energy. Capacitors are discharged. Inductors have no current flowing in them, no magnetic field storing energy. The system is just sitting there static when we first apply our input. And in fact, we're even going to be thinking about there never is a first applying of the input. We're going to think about the input having always been there. I know it sounds weird, but that's what we're going to do. So we'll stop there for this video and look forward to seeing you in the next one. Thanks.